All right, so your 6 groups, each problems to work on. You went through in your groups and you solved your problem, and hopefully you had a little bit of time to discuss what did you find was simple about your problem and what did you find most challenging about it. And I want you to kind of shelve those observations for a moment, maybe jot them down on a pad or something, because we're going to come back to them in just a minute. But just to circle back to what we were talking about before, the various problems that you got in your groups were each kind of representative in their own way of one flavor of what we think of as numeracy. So just to get that definition back on the table, when you think of numeracy, it's about skill and comfort in handling everyday numbers, numbers within everyday context. Lynn Steen, I think, said it best when he said that it's sophisticated reasoning, but using elementary mathematics. That's why this is not really a STEM talk. It's about the simple mathematics, the quotidian mathematics that you find in the world around you, no matter who you are, whether you're in the sciences or whether you're just trying to live an everyday civic life. And numeracy is a big issue in our country specifically. The OECD just came out with a study of developing countries. They looked at 24 developing countries and found that the U.S. adults had third from the bottom level of numeracy among the developing countries that they developed countries that they looked at. And our young people, our 16 to 24-year-olds, were dead last in numeracy skills on that list. This was major alarm bell went off when this study came out earlier this year. Actually, Fareed Zakaria just mentioned this on his GPS program a couple of weekends ago. So this is big news. I mean, I think we've all of those of us in education know that our students are number challenged, but I'm in mathematics that I didn't know it was this bad. And there's a lot of anxiety that goes on around mathematics and a lot of self-identification on how much you are or not a math person. Right? I hear this from students a lot. Oh, I'm not a math person. Well, what does that sentence mean? When someone says I'm not a math person, what are they really saying? I don't like it. I haven't found it enjoyable. It's scary.
And that's okay.
And that's okay. So it's a self-excuse statement, right?
Yeah. I mean, all of these things are possible behind it, but when they say it to me as their math teacher, my experience is what they're really telling me is I'm not planning on doing well in this course, and I'm not going to try either. Yeah.
Yes, right. It's that setting low expectations for themselves, so that if they exceed them, great. But if they don't, oh, that's okay. It's just that I'm not a math person, right? It's inextricably tied to this idea that intelligence is some sort of fixed quantity.
I want to add another dimension to it.
Yeah.
That puts it into the category of talent, not skill. That can be.
That's right. Absolutely.
So I'm not born with it. I can't possibly acquire it.
Exactly. So is mathematics a talent or is it a skill? I think that those who employ this I'm not a math person defense are really seeing it as sort of some blessed quantity, right? Something that people have from when they're born. And if you don't have it, then you're never going to get it. And that there are no strategies and that there are no skills and there's no way to approach the subject in a way that it can be learned. And so it's that setting of low expectations. There's some very more recent studies that are done on math anxiety. And it found that something like, I think it was at least 25% of students at 4-year universities and as many as 80% of students going into community colleges report a very high level of math anxiety, that enough to interfere with their ability to succeed in mathematics courses. So it's clearly a big issue and it has a lot to do with how students respond to setbacks. If you're familiar with the growth mindset and grit theories, it's bad because it's a self-perpetuating loop, right? That when you do math, you will make mistakes that are objectively mistakes and demonstrably mistakes. It's going to happen no matter what. But if a student responds negatively to that, if they see that mistake as some sort of referendum on their intelligence or their character, that makes them anxious. And makes them anxiously seek to avoid any further contact with the subject because it'll confirm this new self-stereotype that they have about themselves. And the more anxious that they are when they actually have to do something mathematical, the less their working memory can work for them. And the worse they do and the more mistakes they make, and then it just feeds in on itself. So math anxiety is this really self-destructive loop that in order to get anywhere on this numeracy problem, I think we have to address it. And finding ways of doing that within the classroom, I think, is place number one. I think that all of us have some ability to impact what happens inside of classrooms where you work with numbers. So let's go back to the problems that you all got in your groups, the 6 different flavors of problem. Can I get, just in unison on the count of 3, each group decide on a representative and shout out the answer that you got to your problem, just the answer on the count of 3. 1, 2, 3.
2.65.
2.65.
Isn't that interesting? You all got 6 different problems and somehow ended up with the same answer. But which is, I mean, I shouldn't tell you this because I should give you the responsibility for checking, but it was the right answer, 265. And that's because each of your problems was the same essential mathematics problem. So here were the problems. Let's see here. So those of you whose problems were labeled with an A on the top, you had problems that looked an awful lot like an algebra problem. Solve for X, right? That's kind of the most abstract form in which I could have presented that problem to you. Those of you with the B's have something that's not quite algebra, but it's not quite a word problem. It just sort of tells you instructively in a narrative fashion what arithmetic to do, and then you carry out that arithmetic. Those of you with the C's had the classic, what we might call a story problem, right? That you had some story about Ted the waiter who's getting hourly wages and tips and knows what his total is and so forth. And from within those levels of context, there were also 2 different types. An arithmetic problem, so A1 had solve for X, and all you had to do to solve for this particular X was do some arithmetic on the left-hand side of this equation. So all you had to do was go straight forward. The end result was what you wanted, and all of the prerequisites you knew. The in-between told you how to do those operations in narrative fashion instead of using notation and symbolism. And those of you with the contextual problem had a question about Ted going home and taking $81.90 and subtracting 66 in tips and then dividing by his hourly wage to find out, dividing by the number of hours that he worked to find out his hourly wage. So those of you that had A1, B1, and C1, you got an arithmetic problem because you didn't have to do any what a math professor would call balancing of both sides of an equation. All you had to do was straightforward computation. Those of you with A2, B2, and C2 had an algebra problem. Solve for X, for example, where the X is actually trapped inside of some arithmetic on the left-hand side of this equation that you have to undo in order to discover the value for X. This is the classic algebra problem. But then there was an in-between version of that where it sort of described that X is some unknown quantity, which, when you multiply it by 6 and add 66, you get 8190. And then the most contextual of them was the algebra story problem, which is, again, all the same arithmetic wrapped up in this problem, just wrapped up inside of the context of Ted and his waiter job, once again. So these were the 6 different problems that all are mathematically equivalent one to another. So now I want you to think back to what you found simple, what you found challenging about the problem that you worked on in your group. And each of you had one of these problems. And take about a couple minutes in your group and decide, compared to the problem that you got, which of these do you think students would find simpler? And which do you think students would find more challenging? So try to situate your problem in that continuum of how successful students are going to be on these 6 different problems. And feel free to use A1, B1, C1, those to sort of identify which problem is which. So take a couple minutes and try and rate your problem versus these in terms of students' ease. But here's what the high school teachers said that they thought students would have the easiest time with. And as you said, A1 and B1 were at the top of the list. And statistically, there was no significant difference in their predictions between these 2. In the middle, they said A2, as you did. Not so bad. Statistically significantly lower performance expectations than A1 and B1. And then statistically significantly worse than that were the last 3, in fact, in the same order that we have them up here, although order doesn't matter inside each of these blocks because they're statistically insignificantly different. So your expectations and the expectations of the teachers in this study are spot on identical. Cool. How did the students actually do? Because they gave these problems to high school students, I think they were 8th graders, and asked them to solve them and then did a study on how well they performed. What do you think they did the best on? B1, which you were right about, but take a look at C1. C1 was the question where Ted is taking his money and subtracting his tips and then dividing by 6 in a narrative fashion inside of a story problem, and students performed it at a statistically insignificantly no better or worse than they did on B1, where they were just being described how to do that same arithmetic, just without the context. So this, I think, is the biggest disconnect in expectations, is the distance between where the high school teachers and you placed C1 and how students actually perform on C1. It's telling. Statistically significantly worse than that were A1, B2, and C2. So A1 was the order of operations arithmetic problem, and then B2 and C2 were the story and the word narrative problems in algebra. But those 3 were all roughly equivalent. And of course, the one that students performed the worst on by process of elimination, and actually quite poorly, 37% solved it correctly, was A2, the algebra, the abstract algebra problem, so to speak. So this, I think, highlights, as they do, as Nathan and Kettinger do in the paper, the fundamental disconnect between what teachers believe their students will do the best at and what students actually end up doing the best at in terms of whether context helps or hinders students' ability to successfully solve. The effect that context often has is it gives students something to latch onto and a reason to care about a problem. So that when they're carrying these numbers around, 81.9 and 66, they have a context they can attach to those numbers to give them meaning. And maybe, just maybe, give those numbers some value. And motivation, as we've been hearing, probably a pretty consistent theme throughout this conference, motivation is strongly fed by feelings of value, that this might be something worth doing for me, and that really helps keep students engaged and motivated. So that's the first phase. That's about how context can help. And now the second thing I wanted to do is give you an idea for how to take some challenging concepts in statistics and in data and be able to use context to get those statistical ideas across. So what it is something that I call an interactive case study. And the idea of an interactive case study is to, again, leverage this context within a problem to teach students not just something about their discipline, but also something about statistics and statistical reasoning as well. Context is nice because, as you were saying in the back, it increases that felt significance for students. This is something that I might actually care to know about rather than doing something abstract. It's very difficult to motivate. You get all the hands that go up and say, when am I ever going to use this? Of course. Context is also helpful when it's culturally informed. There's a classic study of children in Brazil, street vendors that go around and make change all day, but have very little formal training in mathematics, and how those students actually perform on certain number tasks compared to students who are in the school system in Brazil. There are some tasks on which the street vendors perform really poorly, those that actually use specific notation and orthography, and they write numbers in a particular way, because the street vendors have their own way of writing down numbers and thinking about numbers as well. So the street vendors did poorly on those tasks. But on tasks that are more numeracy oriented, the things that we think of as numerate ideas, like being able to compare two quantities to determine their difference, or to be able to think proportionally and in ratios, Brazilian street vendors did far significantly better than their school counterparts on those kinds of tasks, because they had learned all of them from within this cultural context that was meaningful and relevant to their everyday lives, because they're going around and making change and doing currency transactions all day. Context is also helpful because it's a more natural place for students to ask those big, giant, capital Q, critical thinking questions like why, what if, and what else. It's very difficult even for math majors. If I show them an equation and I ask them, well, what if this x were to increase by 2? Even math majors have a struggle with that. But if you can attach a context to it, well, what if Ted got a raise of an extra $2 an hour? Suddenly, that has a context for them to latch onto and makes it easier to comprehend. So the idea of an interactive case study is to take case studies which are often very static, and students have difficulty really bringing those to life, and give them some life and give them a way to ask and answer those low stakes but very high impact critical thinking questions. So the idea is something like this. Here's something that looks like the context problem that you got a minute ago. So what I was looking for was a way to take a problem like this, which is maybe something that's real and authentic from a discipline that you're already teaching in. If you're teaching a public health class, you might take a public health study that has some data in it. And then add some ability for students to go in and experimentally vary some of the numbers in this, right? If I want to, increase his hourly wage, I just go in and click a button and it increases, and so on. Again, that helps the what-if thinking a lot. And then the case study should also recalculate itself on the fly. So if I change Ted's hourly wage from $265 to $365, then everything else on here should change to reflect that. So that's what students get is kind of this experimental platform that lets them focus not on the computations. So if they don't know the order of operations, they can still get some conceptual understanding out of this exercise and focus on the concepts and the contexts rather than the computation. And depending on what you're teaching and how you're teaching it and why you're teaching it, that might be appropriate and it might not be. But especially if you're teaching in the discipline, you don't want to take time out for a math lesson, but you just want those concepts to come across, I think there's a lot of value in this. And it can also help answer why question. I call this session From Practice to Theory, because the idea is by understanding a particular case and asking what ifs and what else's and whys about this case, you also from there understand something about the numerical, the quantitative, the statistical theory behind it. And so what I wanted to wrap up this session with is a chance for you to experience that with your group, once again, on a challenging statistical concept, a statistical confounding concept. So what I have is a short 2.5, 3-minute video explaining a seeming paradox, a contradiction in statistics, and then an interactive case study that you'll interact with on your device, in which I'll ask you to explain what's going on, explain how this seeming contradiction is actually possible. So let's hope the video plays. In Texas, for example, both white students and non-white students outperformed Minnesota and Massachusetts, and yet the overall average score, which these are 4th grade math scores on a national test, the overall scores were higher in Minnesota and Massachusetts than they were in Texas, even though in Texas both white students and non-white students did better than their white and non-white counterparts in Minnesota and Massachusetts. And the question I would like you to answer with this interactive tool in your group in about 5 minutes or so is, how is this possible? How does this work? How can it be that the two groups outperformed in both categories, and yet the overall scores were lower in Texas? So point your browser to the address at the bottom of the screen here, bit.ly/QR interactive1, and with the members of your group, play around with that tool and see if you can discover an explanation for how it's possible. Take about 5 minutes. Frankly, until I put this tool together, I never really understood how Simpson's paradox works. You have the reference, by the way, for this NAEP data is on the last page of your green packet. If you're interested in more of the data, actually the whole paper was dedicated to showing that this Simpson's paradox phenomenon happens way more often than you would expect it to, specifically in this NAEP data, state-by-state test performance data. But I never really understood how it worked until I did something like this. So what did you discover? How is it possible for Texas to outperform in both ethnic categories and yet have a lower overall score?
It's the mix between categories.
It's the mix between categories,
The
specifically.
non-white kids perform less well, so Texas overall performs lower because they have a higher percentage of the lower scoring group.
It's like 56-44, I think, is the breakdown in Texas of non-white to white, whereas Minnesota and Massachusetts, comparatively, are lily white states. So I can say this lovingly because I'm from Minnesota and I teach in Massachusetts. But yeah, so it's that idea of a weighted average, and that's all it is. That's all Simpson's paradox is to be able to get to what happens in a weighted average when your weights are drastically different in one context and another. But I feel like most of the time when you learn about paradoxes like this, you don't learn it like that in the first place. And little interactive experimental tools like this get that message across in a much more efficient way, I think, than...
Would you mind showing, I'm sorry to interrupt, would you mind showing the previous slide with the website that we put in? Yes.
That was these two, right. So if you're interested in how to create interactive case studies like this, the one that you just played with is a Google chart online, which is that was tricky to put together. But some of you have already noticed it's a lot easier to just put one of these together in Excel. Excel has little nifty interactive form controls. If you're interested in that, the web address at the bottom of the page here, bit.ly/ExcelICS, is a 5-minute introductory video I put together for how to create one of these in Excel. There's also a QR Interactive 2, which is a income inequality little online tool you can play around with. It talks about Gini indexes and pie charts to break down wealth quintiles and all of that fun stuff. That's another neat little tool that you can use for this kind of thing. So what I'm hoping you get out of this talk are some ideas for how to take these numerate concepts and bring them to some sort of interactive reality. My dream someday is to build a wholly online course around these kinds of interactive tools, because I think if you ask the right questions, give the right prompts, and provide the right interactive tools, that if students are willing to experiment, then they can really learn a lot. And that's if science has taught us nothing else, it's that experimentation is a great platform for learning. Oh, I'm sorry. Shh, 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 shh.